So we know that we can dehydrate alcohols by treating them with sulfuric acid and heat, but is this really a favorable process? So let's look into that a little bit. So we're going to look at the enthalpy of dehydration. What I have on your course packet is comparing the energy of the reactants and the products. So we have to look at the bonds that are broken and the bonds that are formed and figure out what side is favored. So bonds that are broken, we broke the CO bond. So CO sigma is broken. And we also broke a CH sigma. So what are the energies of those? This is 393 kilojoules. And this one is 410 kilojoules. So together, those add up to 803 kilojoules. So it requires 803 kilojoules of energy to pull those bonds apart. So that's a positive value because breaking bonds costs energy. Forming bonds, what did we form? We formed the CC pi bond, so the CC pi, and we have an OH sigma bond. So the CC pi, or forming bonds that releases energy, the CC pi is worth negative 267 kilojoules, and the OH sigma is worth negative 498 kilojoules. So together, we had to use 803 kilojoules to break those bonds, and we gained 765 kilojoules of energy out of that. So where's our energy balance? If you just look at adding these two things together, we are actually endothermic, so we're going up in energy, 38 kilojoules. We are endothermic. So this is an unfavorable reaction. And you're going to see a lot in organic chemistry that essentially pi bonds aren't as stable usually as sigma bonds. So this makes a little bit of sense. When we're forming more of these pi bonds and we're getting rid of sigma bonds, that often can show that things are not totally favorable. When are they favorable? They're favorable when we have a really good leaving group. An OC bond is pretty strong, but halogens are really stable by themselves. So usually when a halogen's our leaving group, it's a totally favorable reaction. But when we have OH as our leaving group, this elimination often turns endothermic. So alcohol dehydration is an unfavorable equilibrium. I'm sure I write EQ. This is an equilibrium. It is not a unidirectional reaction. So that being said, we often write this with just a forward arrow. And why might that be? It turns out that even though this is an unfavorable reaction, there is a way for us to run this reaction and get a really good yield of product despite the equilibrium lying to this side. So how do we do that? One thing I also want to point out is the heat part. Why would heat be important? Well, this is, as far as entropy is concerned, the randomness, a more random situation is favorable. Well, we have two products, only one reactant, so this reaction in the forward direction increases randomness, which is a favorable thing. And entropy becomes more and more important the higher the temperature of the reaction. So one thing that drives this reaction forward is heat, and then I'm going to rearrange the board and we're going to talk about the second thing that we use to push this reaction in the forward direction. All right, so we learned this is an unfavorable reaction favoring the alcohol as far as enthalpy is concerned. One way we said that we make this system work in our favor is heating it, making entropy more important, and that pushes the reaction forward. But how else can we force the reaction to completion? The top of this page of the course packet says forcing the dehydration of alcohols forward using Le Chatelier's principle. So this is a time where we should review what Le Chatelier's principle is. And it states that whenever a system at equilibrium is disturbed, the system will adjust itself to reestablish equilibrium. So it's going to readjust itself to establish equilibrium. So what does that mean? Well, say we started with all starting material, no product, and we're going to start with 1,000 molecules of starting material, 0 of product. Then we start the reaction runs for a while, and we reach equilibrium. And we're going to say equilibrium, it favors the starting material, and it favors it about 70% to 30%. So at equilibrium, we now have 700 of these molecules and 300 of these molecules. So how do we force the reaction forward? You can see that it is that alkene is there. I promise. Silly lights. Anyway, so how do we push the reaction forward? We remove the product. At that point, we'd have 700 of these left over, and we'd have 0 of these because we just removed all of them. At that point, we now are going to reestablish equilibrium with what was left over, so it's still going to go to a 70-30 mix, and 70% of 700 is 490 molecules of that, and 210 molecules of the product. So essentially, just by allowing equilibrium to establish once and then a second time, we've already cleared out half of the starting material, pushing it forward to the product. And we're not just going to do 2 rounds of this. We're going to do this until essentially we are at the maximum amount of product possible. So then the next question becomes, well, you're saying you're removing this product. Those things might both be liquids, whatever they are. How are you going to remove one from the other? And it turns out that we use physical properties of molecules to separate them usually. So how could we potentially separate these 2 species based on their physical properties? So think about that for a bit. When we talk about physical properties, what are we usually discussing? We usually discuss boiling point, melting point, and solubility. And do we expect that these molecules would have similar boiling points, different boiling points, different solubilities, same solubilities? They should be different in a lot of those things. One of these has an alcohol functional group. Alcohol is allowed for hydrogen bonding. That's going to increase the boiling point. That's going to make it more soluble in water. This has no functional groups. It's totally non-polar molecule. So there's going to be a lot of different ways that we can separate these molecules based on their physical properties. One way could be just based on their boiling point alone. Turns out that this molecule, ethanol, has a boiling point of 78 degrees Celsius. Ethylene, ethylene's the common name, ethene is the IUPAC name, has a boiling point of negative 109 degrees Celsius. So essentially, if we were doing this reaction to push it to completion, all we would have to do is just heat the reaction. Whenever the product formed, it would immediately turn to the gas phase and bubble out of solution. So we would essentially be able to continuously push this molecule to that phase, and then it would go away, and we would continually go through round after round after round of product removal, pushing this forward to the products. So that's how we push these reactions forward, despite them not being favorable when we talk about their bond energies, their enthalpy. So we use Le Chatelier and we use heat.